This is the sharpest image of the sun ever taken, but capturing a clear image of the sun is much harder than it looks. Let me show you why. Imagine it's night time and you thought of taking a picture of Jupiter, so you brought your telescope. Now, in these low light conditions, you need high exposure time. What that means is, if you take a photo of Jupiter by just a click and done, then you will get a really blurry photo of it. But if you wait and let the telescope capture more light, you will get a sharp image. But the problem with the sun is completely different because there is a lot of light, so you need really low exposure time, just tiny fractions of a second. And don't worry, we already have telescopes that can do that. The bigger problem is atmospheric turbulence. Okay, let me give you an intuition about what it is. Do you know that when you pass a light through a glass slab, then it gets bended? This effect is called refraction, and the amount by which this light bends is actually defined by refractive index. But how this will help? The thing is, when light rays from the sun pass through Earth's atmosphere, they get bent. The reason for that is, during the daytime, the temperature changes much more between different layers of the atmosphere compared to nighttime. Because of this, different layers of air bend light by different amounts. You can think of it like many glass slabs stacked together, each bending the light a little differently. And as hot and cold air keep mixing continuously, the sunlight keeps changing direction again and again. This makes the image of the sun look shaky and unstable. It is actually the same reason why faraway objects seems to fluctuate on a hot summer day. So now what? We solve this problem using something called adaptive mirrors. But what exactly are they? Okay, in a normal situation, when light rays are coming straight, the mirror inside the telescope focuses all the light to one precise point and create a sharp image. But when the light gets bent by Earth's atmosphere, the mirror is no longer able to focus all the light rays to a single point, which makes the image blurry. An adaptive mirror tries to bring the bent light back to a single focus point again. Adaptive mirrors actually change their shape to do this. Okay, it might be confusing. Let's see how this actually works. First of all, we know that when a light ray hits a mirror, the reflected ray leaves at the same angle. So the idea is simple. Slightly tilt the mirror so the reflected light goes in the correct direction. In this case, every portion of the mirror will try to adjust itself so that all the reflected rays come together at a single point and forms a clear image. This adjustment and tilting is done using tiny motors attached behind the mirror. Now all of these ideas are incorporated in the Daniel K. Inouye Solar Telescope. This telescope is actually located in Hawaii, and there is a special reason for that. Since Hawaii is surrounded by ocean and the temperature variations are much smaller compared to land areas, basically avoiding the atmospheric turbulence as much as possible. This telescope captures thousands of images of the sun every second and then combines them together to create this extremely clear image of the sun. And this tiny section that you are seeing here actually represents a distance of around 500 kilometers on the surface of the sun. Now, you must be getting a feel that it looks like the surface of a cookie. Yeah, exactly. But what is this stuff in this image? The sun is actually made of plasma. And just like boiling water creates rising bubbles, hot plasma inside the sun rises up to the surface. If you look closely at this cross section, the bright regions show the hot plasma rising upward, while the dark outlines represent cooler plasma sinking back down. So in a way, the sun is basically a giant boiling ball of plasma.